Flare vent system load analysis. Proper sizing of flare and vent systems depends on a thorough understanding of the maximum credible loads they must handle. These loads result from combinations of relief events, emergency depressurization, and operational upsets. The goal is to ensure that the flare headers, knockout drums, tips, and vent stacks can accommodate all expected flow scenarios without creating excessive back pressure or compromising safety. Chasher determining maximum system load. To size headers and downstream piping accurately, the designer must evaluate the maximum flow rate that creates the highest back pressure in the system, not necessarily the highest mass flow, the temperature and molecular weight of the gases, as these influence volumetric flow and pressure drop, the simultaneity of events across process units, particularly during site-wide failures. The analysis must be based on specific worst-case scenarios, rather than adding unrelated contingencies together. Combining independent failures results in unrealistic overdesign and unnecessary capital expenditure. Typical load cases to evaluate. Each process unit or relief source should be analyzed for these key scenarios: total utility or power failure, partial utility failures, e.g., cooling water loss, single equipment failure, e.g., control valve stuck open, emergency depressurization, fire exposure of individual fire zones. The maximum flare load from each scenario must be determined and compared. The most conservative but realistic case forms the basis for system sizing. Accounting for multiple units and common failures. In integrated facilities with multiple units connected to a shared flare system, for a site-wide utility failure, use stat 100% of the relief load from one unit, the most critical, plus 50% of the relief loads from each of the other units. This approach assumes process dynamics and protective controls will stagger the response. Not all relief valves will open simultaneously. Operator intervention and system damping effects reduce peak simultaneity. If two or more units are known to respond simultaneously to a given event, e.g., due to shared cooling or power, their loads must be fully combined for sizing. Fire scenarios and zone-based analysis. When analyzing fire-induced relief and depressurization, assume a fire occurs in only one zone at a time. Evaluate each zone individually, taking all affected equipment into account. Include both fire relief from exposed vessels, emergency depressurization flows from equipment within the fire zone. Avoid double counting where a vessel is both relieved and depressurized. Include the greater of the two loads, or model the dynamic transition between them. Flare load dynamics and back pressure management. Flare header sizing is based not only on flow rate, but on pressure drop through the system. Dynamic analysis may be used to consider line packing during depressurization, temporary increase in pressure due to vapor accumulation, header segment velocities, ensuring they stay below choked flow thresholds. Effects of simultaneous operation of multiple depressuring valves. If validated dynamic modeling tools are used, designers may take credit for pressure equalization and staged flow, which can reduce the required pipe diameter or flare tip size. Flare and vent load analysis is a foundational step in designing a safe and operable relief system. It ensures that under any credible combination of failures, the system can handle the resulting flows without overpressure, flashback, or excessive environmental release. Sizing of downstream piping systems. After determining the maximum flare or vent loads from all credible scenarios, the downstream piping system, including headers, subheaders, and lateral branches, must be properly sized to handle the flow without causing excessive back pressure or compromising relief valve function. Back pressure considerations. Sizing starts from the flare or vent tip, where the outlet pressure is atmospheric or choked, and works backward toward each relief or depressuring source. Pressure drops through each section are calculated cumulatively to determine the built-up back pressure at each valve outlet. Acceptable back pressure limits are dictated by the type of relief device used. Exceeding these limits can cause delayed or incomplete valve opening, reduced flow capacity, potential for valve instability, or chatter. Use of validated pressure drop calculation tools is recommended. When performing these calculations, assume a pipe roughness appropriate for clean service, e.g., 40 millimeters for carbon steel. Adjust pipe diameters as needed to remain within back pressure limits for each valve type. Hash selection of relief valve type based on back pressure. Depending on the calculated variable, built up back pressure, select relief valve types according to these guidelines. 10% of set pressure, use non-balanced spring-loaded valves. 21% of set pressure, fire case only. Non-balanced spring-loaded valves may still be acceptable under specific design codes. For 50% of set pressure, use balanced bellows spring-loaded valves. 70% of set pressure, use pilot-operated valves, provided cleanliness and other service requirements are met. Avoiding overpressure and cross-contamination. In systems with multiple depressuring valves, confirm that flow from high-pressure systems cannot backflow into connected low-pressure systems. Evaluate any interconnected headers or shared vent paths to ensure back pressure does not inhibit relief from adjacent units or zones. Velocity limits and future expansion. To maintain safe operation and accommodate future plant growth, main relief headers should not exceed Mach 0.5 to higher of under design conditions. Subheaders may operate at higher velocities, but should generally stay below Mach 1.0. Keep in mind that choked flow can occur at velocities below Mach 1.0, particularly at elbows, T's, and restrictions. Add an extra 10% back pressure margin above the recommended valve limits when approaching choked flow to ensure safety and stability. Vibration and mechanical loads. High velocities and two-phase flows can induce acoustic and dynamic forces on the piping system. Relief systems must be designed with proper supports, anchor points, and expansion allowances to handle sudden thrust loads from vapor or slug flow, thermal expansion during emergency discharge events. Proper sizing of downstream piping ensures that relief and depressuring events are managed safely without inducing valve instability or back pressure that could compromise protective function. A well-sized system supports operational flexibility, long-term reliability, and regulatory compliance under all credible process conditions. Flow measurement requirements. Monitoring flow in flare and vent systems is essential for operational oversight, environmental compliance, and early detection of process upsets. While flare systems are typically passive safety components, real-time flow data enhances both system visibility and incident response capabilities. Objectives of flow measurement. Flow measurement devices in flare headers should be selected and installed to support the following goals: detecting abnormal flows that may indicate relief valve activation, system leaks, or unplanned venting. Quantifying routine flare losses to support emissions reporting and flare gas recovery initiatives. Monitoring purge gas rates to ensure proper sealing of flare stacks and prevent air ingress. Supporting diagnostics during system testing or equipment troubleshooting. Providing alarm functionality if flow exceeds expected thresholds during normal operation. Instrumentation and device selection. Key factors to consider when selecting flow meters for flare service include high turndown ratio to capture both low purge flows and high rate emergency events, non-intrusive or low obstruction designs to prevent pressure drop or risk of blockage in a critical safety system, suitability for varying gas compositions, temperature ranges, and possible two-phase conditions during depressuring, robustness for long-term operation in challenging service environments, including potential fouling or corrosion. Ultrasonic flow meters are commonly recommended due to their high accuracy over a wide range of flow rates, minimal pressure drop, non-intrusive installation, clamp-on or inline options, suitability for dirty, wet, or changing gas streams. Installation considerations. Proper installation is critical for reliable performance. Ensure adequate straight run lengths upstream and downstream of the meter to avoid flow profile distortion. Consult manufacturer's guidelines. Avoid creating low points in the piping near the flow meter, which could accumulate condensate and affect readings or damage the device. Install meters in elevated, accessible, and well-drained locations, especially when condensable vapors or liquid carryover are expected. Use redundant or bypass arrangements only when necessary, as flare lines should remain as simple and direct as possible. Maintainability and access, devices that can be maintained or replaced without shutting down the flare system, especially in continuously operating facilities. Include monitoring capability in the control room or distributed control system, DCS, for real-time operator feedback. By incorporating accurate and reliable flow measurement in flare and vent systems, operators gain critical visibility into process safety behavior, emission performance, and operational health, while maintaining the passive, fail-safe nature of the relief system itself. Nashbed. Flare pilot requirements. Flare pilots are essential to ensure continuous and reliable ignition of flare gas under all operating and environmental conditions. A flare without a functioning pilot poses serious safety and environmental risks, especially during emergency releases. The pilot system must therefore be robust, stable, and independently monitored to guarantee ignition when required. Key functional requirements. Stable combustion must be maintained in all weather and flaring conditions, including high wind speeds, varying gas flows, and intermittent flare usage. Multiple pilots are required to ensure redundancy and complete flame coverage. For flare tips up to 400 millimeters diameter, at least 2 pilots. For flare tips larger than 400 millimeters, at least 3 pilots. Each pilot must be fitted with a dedicated ignition line to allow individual startup and reignition. Pilot positioning and flame stability. Pilots must be positioned so they are not engulfed by the flare flame, even under strong crosswinds. Their layout must guarantee effective ignition of the flare tip, regardless of flow rate or flame lift. Wind deflectors or shields may be used to protect pilot flames from blow-off. Material and construction standards. Pilot burners and supports must be constructed of corrosion-resistant and high-temperature materials. Pilot lines, AISI 321 stainless steel, minimum. Top 4 meters of pilot lines, AISI 310S Incolloy 800H or equivalent, to withstand direct flare radiation. All thermal expansion and mechanical stresses between pilot lines and the flare stack must be accounted for with appropriate supports and expansion flexibility. Kinashart, advanced pilot technologies. Venturi-type nozzles are recommended for improved flame stability. Enhance air entrainment, lower gas consumption, deliver high-velocity flame jets less prone to wind blowout. Pilot gas flow must be stable and clean, with consistent composition and suitable Wabi index to prevent flame instability. Fuel gas and air supply requirements. Fuel gas and ignition air must be dried and filtered to eliminate the risk of line blockage due to condensation or particulate buildup. Hydrocarbon and water dew points must be below the minimum ambient temperatures expected on site. Use dedicated stainless steel pilot gas lines downstream of any carbon steel supply sections. Pilot lines must be installed with no low points or pockets that could collect liquids. Handfrench, monitoring and alarming. Each pilot must be monitored using a robust K-type thermocouple capable of withstanding direct flame and radiation exposure. Failure of any pilot must generate a control room alarm with clear identification of the affected pilot. Thermocouples should be properly insulated and supported to prevent failure under thermal stress. Ignition system redundancy and maintainability. All pilot burners must be individually ignitable using dedicated ignition lines. Systems should allow for manual reignition from a safe location with visual access to the flare tip. In critical applications, consider dual ignition systems, e.g. flame front generator with manual backup. Flare pilot systems must be treated as safety-critical components. Their design and maintenance directly impact the reliability of flare ignition during emergency events, where dependable performance is not optional but mandatory. Flare ignition requirements. A reliable ignition system is essential to ensure that flare pilots ignite on demand and maintain stable flames under all operating conditions. Ignition failure during a flare event can result in unburnt hydrocarbon release, toxic vapor dispersion, and significant safety or environmental consequences. Therefore, the ignition system must be designed for high reliability, durability, and maintainability. System type and design principles. Flame front generator (FFG) systems are strongly recommended due to their proven reliability, ability to deliver high-energy ignition, and maintainability while the flare system remains live. Each pilot must be ignited via a dedicated ignition line to avoid cross interference and ensure independent ignition control. Ignition control and operation. Ignition must be manually initiated from a safe location, typically at grade level, with visual line of sight to the flare tip to confirm pilot light up. The system must be capable of reliably igniting the pilots under design wind conditions and varying fuel gas compositions. The ignition circuit must deliver a stoichiometric air-fuel mixture at the ignition point. This requires carefully designed restriction orifices, accurate air and gas supply pressure control, proper mixing to produce a stable flame front, fuel and air quality requirements. Both ignition gas and air must be filtered and dried to prevent blockages in small bore ignition lines, condensation that could extinguish the flame, formation of corrosive or explosive mixtures. The dew points must be below the minimum ambient temperatures encountered on site. Ignition line layout. Ignition lines must be routed to avoid pockets or low points where liquid can accumulate and obstruct flow. Use corrosion-resistant materials such as stainless steel for ignition lines with proper support and flexibility to accommodate thermal expansion. Operational reliability and maintenance. Ignition systems must be robust enough to reignite extinguished pilots quickly and safely, even under challenging process or environmental conditions. System components should be accessible for inspection and maintenance without shutting down the flare. Where backup is required, a bottled gas ignition source may be provided for use during system startup or recovery from failures. By implementing a reliable, well-maintained ignition system with dedicated ignition lines, safe remote operation, and robust air-gas supply control, the flare system is ensured to function as intended, igniting relief flows quickly and preventing unburnt hydrocarbon emissions. Ignition reliability is a cornerstone of flare system integrity.